All right, so in lesson 1, we were looking at the Malthusian model of population growth for the US population. And it assumes that populations grow at a rate proportional to the size of the population. And for the US population, it matches the data really, really well up until about 1860. And then it starts overestimating by more and more and more. Okay? So we need to adjust our assumptions about how populations grow, because this model didn't work that well. So what happens is that when the population gets bigger, that model no longer holds. It works for small populations, but so when the population is small, the rate of growth is proportional to its size. But then as the population gets really large, it becomes too large to be supported by its environment, right? There's not enough food, there's not enough space, there's not enough resources for the population to continue to grow so quickly. So it says if the population is too large to be supported by its environment and resources, the population will then decrease. And then the rate of growth will be negative. So we're going to go through the modeling process again, having adjusted our assumptions. So again, our most important variable here is P, population size. Okay. And there's sort of a hidden parameter in here. There's some critical amount, right? So if the population is small, the population grows fast. It grows proportionally to its size. But if the population is too big, the size of the population will start to decrease. So there's some like critical value after which the population is too big. We call it a carrying capacity. So let's just call it, we'll call it N, right? Some capital N. It's not a variable, it's a parameter. It's some value, right? Some number at which the population is now too large. So we'll call this the carrying capacity of the environment. Okay, so I need to write a model, right, that captures these two assumptions. So what I want is for dp dt, which is the rate of growth of the population, I want it to be what do I want it to be? Yeah, I want it to be positive when yeah, I want it to be positive when p is small, right? I want it to be approximately 0 when p is what? Approximately n, right? So if once it hits the carrying capacity, it'll just stay there, right? When p is approximately hitting the carrying capacity. And I want it to be negative when p is bigger than n. Right? When the population goes over the carrying capacity, I now need the rate of growth to be negative, to decrease. All right, so I got to write an equation that captures those three pieces. So I already know I can capture number 1, right? I can capture this dp dt is positive when p is small. So I've got dp dt equals kp. That was the Malthusian model, and that captures exactly what we want for assumption 1, that it will grow proportionally to its size. But that only works if p is small. So I'm going to add another factor here. I'm going to multiply by something. I'll just tell you what it is, and then we'll show that it satisfies all these wants here. 1 minus p over n. All right, so p over n, if p is approximately n, right, then p over n would be about 1, right? If they were equal, this whole factor would be 0 and dp dt wouldn't change, right? So that captures this piece. Okay. When p is really small, like if the numerator is a very small number here compared to the n, then this factor is approximately 1, and I have kp, right? So dp dt equals kp when k is small. And then when p is large, if p is bigger than n, then p over n is going to be a number bigger than 1. So 1 minus number bigger than 1 will be negative. And now my rate of growth is negative. So you agree that this, it is hard to write a model that captures those assumptions. Like if I wanted to come up with that from scratch, but once I see it, I can say, okay, yeah, that satisfies all the assumptions that I want. All right, so rather than giving you the solution to this logistic equation, this logistic model, we're just going to think about what the solution functions will look like qualitatively, right? So I'm going to start by looking for equilibrium solutions. Equilibrium solutions are constant functions that satisfy the differential equation. All right, so what is the derivative of a constant function? 0, right? The derivative of 5 is 0, right? So if I want constant functions, looking for constant solutions, those happen when the derivative, dp dt, equals 0. And I happen to know the derivative, right? That's exactly what the model is. It's the derivative. So I take my model, kp, times 1 minus p over n, and set it equal to 0. And I'm going to solve for p. I'm looking for solutions p of t, and its derivative will be 0, which means that the function will be flat. So this is a product, right? When you multiply two things together and the answer is 0, set each factor to 0 separately, right? So you get kp equals 0, or 1 minus p over n equals 0. Solve each of these. So p of t equals 0. That's a solution to the logistic equation. That makes sense. If there are no people, then the rate of growth will be 0. All right, and then if I solve this one for p, I get p of t equals n. So when I hit the carrying capacity, my rate of change is 0, which is how I designed this model. I wanted it to be that if I was at the carrying capacity, the population would not change. It'll just stay at the carrying capacity. So it makes sense that its derivative would be 0. All right, so those are my equilibrium solutions. So if I want to sketch them, so this is t and p. I have one solution at 0, it just stays 0 all the time. And I have another equilibrium solution at n. So if you start at n, you just stay at n forever. What do you think happens if I start down here, somewhere between 0 and n? It approaches n. It's going to grow quickly at first, right? Exponentially at first, because the population is pretty small. And then it slows down as it reaches the carrying capacity. What if the population starts larger than n? Like I just dropped, 500 rabbits in an environment that can only hold 300. It's going to go down to n. What if I start really close to the carrying capacity? It grows slowly towards the carrying capacity, yeah. So I know exactly what these solutions look like, even though I don't have a formula for the solution curves, right? Like I don't have a y of t equals some formula with t's in it, but I know exactly what it looks like. So this is called a qualitative solution. So we know a lot about the solutions, even without finding an analytic solution, but we'll be able to solve it analytically next class. Tuesday, we'll come up with a formula for those graphs. So next, we're going to adjust our assumptions about how populations grow again. So the logistic model is much better than the Malthusian model, but it doesn't take into account the fact that there are predators, right? So there's predators and there's prey. So just to simplify these things, we're going to call it rabbits and foxes for the prey and the predators. They influence each other, so we're going to try to model both populations at the same time. So here are our assumptions. If no foxes are present, the rabbits are going to reproduce at a rate proportional to their population. And we're not going to take into effect overcrowding here. We're just going to say they can multiply as much as they want. The foxes eat the rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. So how often they see each other is how often foxes eat the rabbits, or it's related. So without rabbits to eat, the fox population will decline at a rate proportional to itself. They'll die off because they don't have any food. And the rate at which foxes are born is proportional to the number of rabbits eaten by foxes. So the more food they eat, the faster they reproduce. And the number of rabbits eaten by foxes is given by the second assumption, proportional to the rate at which they interact. So I want to translate these 4 assumptions into a model. So my important variables are R and F, the number of rabbits and the number of foxes. So let's start with that. Number of rabbits. F is number of foxes. Now I have some parameters because I have a bunch of proportional to statements, right? Proportional to, proportional to, proportional to, proportional to. And every time you have a proportional to statement, you've got this constant of proportionality when you try to write an equation for it. So I'm going to have 4 constants of proportionality. So let's call them alpha, beta, gamma, and delta. So those are constants of proportionality as I try to translate these things into equations. Okay, so I'm going to translate each bullet one at a time. So the first one talks about how the rabbits change. Right, so the rabbits reproduce at a rate proportional to their population if there are no foxes. So let's just write, assuming there are no foxes, that's just the Malthusian model. So dr dt, I'll write it over here. Dr dt equals alpha r. So I'll use my first constant of proportionality, alpha. Malthusian model. But then it says, the next bullet talks about what happens if the foxes eat the rabbits. So the foxes eat the rabbits, the rate at which the rabbits are eaten, so this is how it grows, this is how the rabbits grow, but then their population declines as they get eaten, so I'm going to subtract how often they're eaten. And that happens proportional to the rate at which they interact. So we need a constant of proportionality, we use beta. And then I need some way to mathematically show they're interacting. So I'm going to use the product of R times F. There's more than one way to do this. You could do R plus F, right? But I'm just going to multiply the number of rabbits times the number of foxes. And that's just going to be a number that shows how often they interact. More rabbits means that product will go up. More foxes means that product will go up. So more of either animal means they interact more. And so that's my interaction term, RF. You could also add them, but using a product has some advantages. Yep. Not really. It's just yeah, it's just the beta would change. Yeah, yep, exactly. Okay, and so now I'm going to write an equation for foxes. Okay, so I've got the last 2 bullets deal with how the fox population changes. So I have df dt equals, so without the rabbits to eat, the fox population will decline at a rate proportional to itself. So declining means it's negative. I'll use my next constant of proportionality, gamma proportional to itself, f. And I'm just going to say that these parameters are all positive. So I have to put the negative sign there to indicate that it's decreasing now. And then my last bullet says the rate at which foxes are born. So we're now increasing the population of foxes. That's proportional to how often they interact. So I'm going to add my last constant of proportionality interaction term, RF. Okay, so because they interact, we have to write those two models together. Those equations go together, and we call that a first order system. It's first order because it only has first derivatives in it, and it's a system because there are two of them. So the solution to this first order system is a pair of functions, one for rabbits, one for foxes. And since the two functions depend on each other, you can't just solve one and then solve the other. You have to solve them simultaneously. It turns out there is zero analytic way to do that for most parameters. You just can't solve it. So we have to use either qualitative or numeric techniques to study the solution. So we just talked about qualitative with graphs. So we're going to look at a quantitative or numerical way to do this. All right, so one way to study solutions numerically is to pick some initial values for R and F. Like just say, like, what if we started with 10 rabbits and 10 foxes? Like, what happens to them based on these assumptions? So I'm not going to use 10, but I'm going to say just rewriting my equations. And I'm going to use the easiest parameters possible. Instead of alpha, beta, gamma, and delta, I'm going to use ones, right, just to make this the easiest as possible. So I have R minus RF, and df dt is negative F plus RF. And then we're going to start with some random initial conditions. If we start with, at time 0, we have 12 rabbits and 2 foxes, how does this situation evolve? What's going to happen to the rabbits and the foxes? Well, I can at least approximate it because I know how the rabbit population and the fox population changes, right? I know the rates of change, so I can figure out how much it changes at each time interval. At least I can estimate each time interval. All right, so let's see. After one day, so I need to know how much the rabbit population changes and how much the fox population changes. So R of 0 is 12, F of 0 is 2. So I'm going to replace my R's with 12s and my F's with 2s to calculate a dr dt and a df dt. So I'm putting in 12 for R and 2 for F. So this is going to be negative 2 plus 12 times 2. So that's negative 12, and this is 22. So this is the change in the number of rabbits and the number of foxes. So I now know R of 1, right? Take the previous amount. I started with 12, right? And then I lost 12 rabbits because dr dt was minus 12. So this is my units on dr dt is rabbits per day. And my units on df dt is foxes per day. Because my equation for df dt is negative F. So R of 1 is R of 0 plus the change in R, how much it changed in one day. So this is 12 minus 12, which is now 0 rabbits. Wiped them out in one day with just the 2 foxes. So F of 1 is F of 0 plus the change in F, which is 2 plus 22. They now have 24 foxes, but what's going to happen to them next? They're now going to die off because there's no rabbits left. Right, so I could do this again. I could now take my 0 and my 24, plug into drdt and dfdt, and figure out how much they're going to change by for the next day. So let's just do that. I will never ask you to do this by hand for a system, but just so that you have an idea of what's happening. So now drdt is r, which is 0, minus r times f, so 0. So this makes sense because there are no rabbits left, so the change in rabbits per day should be 0, right? They can't grow or decline, there aren't any. And then df dt is negative f, so negative 24, plus r times f, which is negative 24. So that's how much they changed by. So now r of 2 is r of 1 plus delta r, which is 0 plus 0, which is still 0 rabbits. But f of 2 is how many we had at the first one, plus the change in f. So that's 22 minus 24, which is negative 2, which doesn't make any sense because the model doesn't know that this is modeling rabbits and foxes, right? Oh, yeah. Okay. Thank you. Good. 24 minus 24. I now have 0 foxes. So within 2 days, both populations are wiped out. Yeah, right. So the parameter does. Exactly. Yeah. That's a really good question. So yeah, I used the easiest possible parameters to make the arithmetic easy. But yeah, you would adjust the parameters to make this timeline make sense. Yeah. But not rabbits. Yeah. So if I wanted to, if there wasn't a situation where both animals go extinct like really quickly, this process could take a long time. If I had to do 10 steps of this, like, oh my God, right? You don't want to do that. So a computer program, it would be really, really helpful. And in fact, writing an Excel spreadsheet to do this for you is your first project. All right, so we've seen 3 models for population growth: the Malthusian model, the logistic model, and a predator-prey model. We've seen 3 techniques for studying solutions: analytic, which is when you just deal with formulas, right? All we've done so far is checking that a function is a solution. We'll be able to actually find solutions next class. Qualitative techniques for studying solutions, where you can just sketch pictures of the solution without knowing anything about the formulas. And numerical, which is what we just did with the rabbits and foxes. So the next 3 sections of the text go further in depth into those 3 techniques. So next class, we're going to talk more about analytic solutions. All right, so that finishes up the lesson 2 lecture.